Okay, so let's go through Chapter 12, Problem 27. Let's quickly read through the problem. We have a 950 kilogram cylindrical can buoy which floats vertically in seawater. The diameter of the buoy is 0.9 meters. Calculate the additional distance the buoy will sink when an 80 kilogram man stands on top of it. Okay, so let's try to interpret that, those words. Let's draw a picture. I'm going to draw the seawater, and I'm going to draw a buoy. All right, it's a cylinder, can-shaped buoy, which is floating vertically. So I'll draw something kind of can-shaped floating vertically. Okay, and then it tells me that somebody stands on top of this buoy, and when it does so, the buoy sinks more. All right, so let's see what happens when this person gets on top of the buoy. There we go. Okay, and okay, here's the person standing on top of that. So okay, that's kind of a diagram of what's going on. Let's also write down our knowns. We know that the mass of the buoy is 950 kilograms. We know its diameter is 0.900 meters. Okay, that tells me its radius is 0.450 meters. Okay, and then it also tells me that the mass of the person is 80 kilograms. Okay, so I don't actually know the size of this buoy. The problem doesn't tell me this dimension. It doesn't tell me the length of that buoy, but I do know the diameter and radius. Okay, so how do we solve this problem? Well, first we have to recognize we have something floating. That means we have to add in the principle of buoyancy, and that kind of gives us a clue that we should think about Archimedes' principle, what causes something to float. And we also should recognize that buoyancy is a force. So really this is a force problem. We should treat it the same way we treat any force problem. We should draw a free body diagram. We should write down the sum of the forces and apply one of Newton's laws to solve for any unknowns. Okay, so I'm going to solve this first in a somewhat longer way than is necessary, but I think it'll be a little bit more clear that way. So the first thing I'm going to do is try to figure out the volume displaced by this buoy. Okay, why do I want to know that? Well, we know that Archimedes' principle tells us that the flotation force, the buoyancy force, is related to the volume of liquid that you've displaced. Right? It's related to the weight of the liquid that you've pushed out of the way. So I'll try to draw in that volume that is displaced. Okay, so that is the amount of volume of the cylinder which is underwater. Right? That is the volume displaced by the cylinder, which is less than the volume of the cylinder. Right? So the cylinder is floating, but some of it is above the water, some of it is below. So the volume it's displacing, the volume of water it's pushing out of the way, is less than the actual volume of the cylinder. Okay, and I know that the buoyancy force, we use a capital B for that, is related to the weight of the water that would be where the cylinder is now. Okay, and the formula for that is it's the density of the liquid times G times the volume displaced. Right? This is the volume of the liquid that got pushed out of the way. This is the density of the liquid, and this is G, 9.8 meters per second squared. Okay, so that's the equation, but we also need to understand conceptually where does this buoyancy force come from. Okay, so my first goal is going to be to figure out what is the volume displaced by the cylinder. I don't know the actual size of the cylinder, I don't know the volume, but I can figure out the volume of water that's been pushed out of the way because I know the weight of the cylinder. Okay, and let's go through that. So as I told you, buoyancy is a force. We should treat this as a normal force problem. Let's draw a free body diagram for that buoy. Right, there's one force in the plus y direction, that is the buoyant force. Okay, and there's one force in the minus y direction, that is a weight. Let me make sure I define a coordinate system. Define plus y to be up. There's two known forces, the buoyant force and the weight. Right, the force of gravity is pulling down on the buoy, but it's not sinking. because there's this other force which is canceling the force of gravity, and that's the buoyant force. Okay, from my free body diagram, I know I can write down Newton's first law, right? The sum of the forces in the y direction acting on that buoy have to add up to 0. Right? This buoy is not sinking, it is not accelerating, so I know there must be no net force acting on that buoy. Directly from the free body diagram, I can figure out what my net force is. I have one force in the plus y direction, that's my buoyant force. I have one force in the minus y direction, that's my weight. Right, so I can very quickly find out that the buoyant force must be equal to the weight of that buoy. Okay, and now I know the formula for buoyant force, I know the formula for weight. Formula for buoyant force is, again, the density of the liquid times g times the volume displaced. The density of the liquid, in this case, is the density of seawater. That's something we're going to have to look up. G times the volume displaced is equal to, the formula for weight is mg. Right, this is the mass of the buoy. Okay, and note that g cancels out, and I can solve for the volume displaced. It's just the mass of the buoy, right, divided by the density of seawater. Okay, so we end up with a pretty easy formula. We know the mass of the buoy, we know the density of seawater, and therefore we can figure out the volume of seawater which has been displaced by this buoy that is floating there. Okay, and let's plug in. The mass of the buoy is 950 kilograms. The density of seawater we have to look up in the table in their chapter. It's 1,030 kilograms per cubic meter. Okay, seawater is slightly more dense than lake water or tap water, which has a density of 1,000 kilograms per cubic meter. Right, you float a little bit more easily in seawater. And when we do this, we find the answer, not the answer to the problem, but we find the volume displaced by just the buoy, and that's 0.9223 cubic meters. Okay, so that's neat. We don't know anything about the actual size of this buoy, but we can figure out how much of the buoy is underwater, right? We know the volume of the buoy, which is underwater, or the volume of water which has been displaced by that buoy. Okay, and now we can figure out the volume displaced in the second case over here. So let's say now this person steps on the buoy sinks, and so now the amount of water which has been displaced is larger. Okay, so let's figure out that now. Right, let's call that maybe volume displaced by buoy plus person. How about that? So we can use the same formula we just figured out, actually. Because the framework will be exactly the same. We can still draw a free body diagram, still have buoyant force up and weight down. It's just now the weight down is going to be a little bit bigger because now we have to consider the weight of the person plus the weight of the buoy. Okay, so let's just, again, we can use this formula we derived already, and the volume displaced by the buoy plus the person must be equal to the mass of the buoy plus the mass of the person divided by the density of seawater. Okay, so this is just 950 kilograms plus 80 kilograms divided by 1,030 kilograms per cubic meter. And when you do that, you get a nice even 1 cubic meter of water has been displaced. Okay, so this is the volume displaced by the buoy and the person. This is the volume displaced by just the buoy. Okay, and so the question is asking how much additional distance will the buoy sink when an 80 kilogram man stands on top of it. So the question is asking to figure out, let's see. So this is the volume which was originally, this is the volume which was originally displaced by just the buoy, and then once the person stood on that buoy, the buoy sank a little bit more, so now this additional volume is underwater, right? And so we can subtract, because we know this volume, we just found that, and we know this total volume of water which is displaced. We can subtract to figure out this volume, which is the volume displaced just by that person standing on the buoy. Okay. If we know the equation for the volume of a cylinder, that will enable us to figure out this distance. Just call that h. Right? That's what the problem is asking. If I draw kind of a line on this buoy for the water height before the person is on it, and then see where that line is after the buoy sinks, I want to figure out how much further did this buoy sink down when that person stood on that buoy. Okay, so let's first figure out this volume of just how much more volume was displaced when this person stood on it. Once we do that, we can figure out the depth of that volume. Okay, so we know the volume displaced by just the buoy. We know the volume displaced by the buoy plus the person. So if I want to know the volume displaced by just the person, well, that's the volume displaced by the buoy plus the person minus the volume displaced by just the buoy. Okay, so that's 1 cubic meter minus 0.9223 cubic meters. And so that tells me the volume is 0.0777 cubic meter. Okay, so this is the volume of water which was displaced when that person stood on top of the buoy. Okay, and once I know that, I also know that the volume of a cylinder in general is equal to pi r squared h. Right, the volume of a cylinder is the area of a circle times the whatever dimension this is, right? If this distance is h and this is r, the volume of a cylinder is pi r squared h. Okay, so this is some volume of water, which again, as this person got on the buoy and it sank a little bit, we have a cylindrical shaped volume of water, which is got a side length of h and an area of pi r squared. So therefore, using this formula, I can solve for h. It's the volume of the cylinder. In this case, the volume of the cylinder is volume of the displaced by just the person divided by pi r squared. Okay, and so plugging in, we find that that buoy has sank an extra 0.122 meters. Okay, and that is the answer that they're looking for. So I went through that somewhat a long way, but I hope it was clear. The most important thing from this problem is this procedure, where you recognize anytime you have something floating, you should apply Newton's laws. If something is not accelerating, which something which is floating typically is not, the sum of the forces must be zero, so we can always figure out what the buoyant force is and solve for an unknown with that. Okay, I just want to note quickly that I didn't have to go through all the trouble of finding the volume displaced by just the cylinder or the volume displaced by the person plus the cylinder. I could have in one step just found the volume displaced by just that person stepping on the cylinder, right? The volume was in this kind of blue region here. Right? I could have done that in one step because I know, again, that the sum of the forces acting on this buoy must be equal to zero, and I know that whatever buoyant force is supporting the person must be counteracted by the weight of that person. So no matter what, I'm going to end up with the same formula down here. The volume displaced by just the person is just going to be equal to the mass of the person divided by the density of seawater. Right? And so when we plug into that simple formula, we should get the same answer we got down here from subtracting. We should get 0.0777 cubic meters, and from that you can again find what the height of that cylinder is, 0.122 meters. Okay.